Okay, so we are through Units 1 and 2. They tend to be the toughest of the units in Physics 20. Right? It does tend to be a little bit easier going forward from here. That said, Unit 3 on circular motion constitutes the bulk of what you will need for the West Edmonton Mall assignment, because so many rides involve loops and circles and such. So the stuff we're going to talk about here over the next few weeks is going to be pretty important for that. Okay, we will probably finish this unit right around the end of November. Okay, maybe first week of December, and then we'll be starting into waves and periodic motion. We won't finish that obviously before Christmas, okay, but we will finish it shortly after we get back, and then have a unit exam and hopefully some time for final exam review after that. All right, so for today, we need to look at what uniform circular motion entails. Okay, so what it is, how it happens, and the relationship between period and centripetal velocity. So some new terms, okay, that we're going to be going over. Now, quick review, because a lot of the stuff from Unit 2 about Newton's laws applies to circles. Right? Not in the same way like, having to figure out net force and all that kind of stuff, but just the laws themselves. Okay? What does an object do if there's no net force acting on it? Nothing. It may do nothing, or it may continue to travel at a constant velocity. If it's traveling at a constant velocity, what does that look like? Right, a straight line. So, in this unit, we're going to be talking about something that's traveling at a constant speed, but moving in a circle. How are those two things possible? According to Newton's first law, those two things shouldn't be possible. Traveling at a constant speed means you're not accelerating. But if you're traveling in a circle, no. Okay, if I'm traveling in a circle, my direction is always changing, agreed? Okay, and any change in direction requires a force. Okay, with that idea. Well, actually, the forces don't cancel out. It's in the wording. Newton's first law says something undergoing, something with no net force acting on it travels at a constant velocity. If something's moving in a circle, it's not traveling at a constant velocity. It might be traveling at a constant speed, but not at a constant velocity, because velocity is vector. Okay? In order for something to move in a circle, there has to be something pulling or pushing on it, constantly changing the direction in which it is traveling. That means it is undergoing, at all times, uniformly accelerated motion because of a net force. Now, if something's going to travel in a circle, I'm going to go back to my getting this. Okay? What's keeping this thing moving in a circle? Okay, but my hand's not touching the tape. Force? Okay, sort of. There actually is no such thing as centripetal force. But we'll talk about that in a minute. There is centripetal force, and what is providing that? The string. Okay, there's tension in the string. Which way is the string always pulling? In. Yeah. If it was pulling out, what would the tape do? Fly out, right? It can't be pulling out on the tape, or the tape wouldn't do this. The only reason the tape is doing this is because the tape is constantly being pulled towards the hand, which is the center of this circle. Everybody follow me on that? Now, if I was to let this go, I'm not. Okay? If I was to let this go, what path would it follow? Exactly. It would follow a straight line. Okay? Straight line from the point where I release it. Okay? So if it's coming around here and I let it go, straight line off that direction. Just like the puke that comes out of people's mouths on the swing of the century. Okay? Because once it exits their mouth, there's no force to keep it moving in a circle. Keep that in mind if you're standing there observing and keeping time. Don't worry, the spray radius is inside of the fence. Okay? Shouldn't get it on you unless you're actually inside the ride, which you should not be. Okay? It also means, though, that you shouldn't get hit by it if you stay on the ride. Okay? As long as the person is not inside of you. Remember, there's 3 rows of seats. Okay? If you think you might get sick, be on the outside. if you're worried about somebody being sick, stay on the inside, okay? Because if they're on the inside and they go over their shoulder to puke, they could get you, okay? Not likely, but they could, okay? So if you want the puke-free zone, it's the interior seats, not the exterior seats. All right. So uniform circular motion, okay, is the motion of an object traveling at a constant speed on a circular path. Okay, so as we can see here, this is kind of like the tape twirling that I was doing, except it's a model plane. Okay, the speed of the plane is constant. Okay, it's not changing, but its vector obviously always is. We can see from the arrow here that when the plane's over here, the direction of the plane is that way. Okay, when the plane's here, the direction of the plane is this way, and so on. It's always changing direction, and the only way to turn something is to apply force on it. Okay, the same is true if you're rounding an icy corner. Okay, what force keeps you in a corner? Friction. If it's really icy, then there's not very much friction. If there isn't enough, and you start to slide, you slide in a straight line. Okay? I don't recommend that be something you try. Okay? You don't want to do that. Okay? But it is true. If you start to turn and there's not enough friction, you'll just slide in a straight line. Okay? Watch Canada's Worst Driver sometime and you see them do that all the time. Okay? And it's entertaining also. All right, we're going to look at a few examples of it, though, that I have videos on that are also very entertaining, because I like watching stupid people get their come-ons. Yeah. Okay, so if we're looking at something moving around and around in a circle, and we want to calculate how fast it's going, okay, then we can use a formula that we're actually fairly familiar with. Since it's moving at a constant speed, I just need to know the distance it travels and the time it takes to do it. Right, okay with that? Right, that doesn't change. Except that now the object's traveling in a circle. So, what do we call the distance around a circle? Around it, the circumference. Right, okay? All right, so the circumference of the circle would be the distance traveled. How do I calculate that using radius? Not pi r squared, that gets you the area. 2 pi r, or pi times diameter. The other way. Okay, using radius is 2 pi r. Okay, and then we got to introduce a new term. The time it takes for one cycle of anything, and this unit will be the time it takes to go around the circle one time, is called the period. And it's symbolized by a capital T. Okay, so the time for one orbit, or one cycle, or one oscillation is referred to as period in physics, symbolized by a capital letter T. Okay. So, calculating the speed of something moving in a circle only requires us to know the size of the circle and the time it takes to go around the circle one time. V equals d over t, but applied to circular motion. Okay. Everybody all right with that idea? Right. So this formula here is on your formula sheets. Okay, you can check it out, but it is there. So if we want to look at like a practical example of this, okay, a tire balancing machine is a practical example of an object moving in a circle. Right? Right now, of course, the time of year where all of us are getting our winter tires put back on. Okay, so we have to balance tires when we put them on a wheel. The reason for that is the process by which tires are made is not 100% accurate. Okay, basically, they take liquefied rubber, pour it into a mold, and let it cool, and then remove the mold, and there you have the tire. Now that process doesn't always distribute the rubber equally. So some parts of the tire may be slightly heavier than other parts of the tire. And that can be a problem if you're driving down the highway. Anybody ever been in a car where when they get to a certain speed, the car starts to shake? Okay, that is because the wheels or tires are not balanced properly. Okay, and it can actually be A, dangerous because it can cause you to lose control, and B, really hard on the suspension, because it's constantly rattling. It's hard on the ball joints and things like that. Okay? So you want to have your tires balanced. So what they do at the tire shop is they put it on this balancing machine, which is spring-loaded, and they just started spinning. And if there's any weight distribution that's wrong, the tire will start to oscillate, just like it does when the car starts to shake. And the tire balancing machine can detect that and knows where the imbalance occurs. It'll stop the tire and tell the operator where to set weights. Okay? Now, weights come in two different types now. Okay, so if this is your wheel, okay, sometimes they have a weight that kind of goes inside and then comes up over the edge of the rim, and it kind of looks like this. Okay, and so it's just got this little tab that sticks to the inside of the wheel. Other times, now they use stick-on weights, and they'll just put these little squares on the inside of the wheel, okay, to put more weight on that side of the wheel and offset anything from the tire being imperfect. You can check that out on your car. Okay, you'll find those in there. Okay? And this can happen as well if you're traveling in like deep, wet snow, and snow gets inside the rim while you're driving. Okay, if it ends up on one side of the rim, it puts more weight on one side of the rim, and when you get up to speed, your car will shudder. You'll have to pull over and pull the snow out of your wheel, because it can actually help like that. All right, now you know how tire balancing works. Important. Now, what we want to do is figure out the speed at which the outer edge of the wheel is moving. Now, we talked about a new term here, and that was period. Okay, so period, like we said, is symbolized by big capital T, okay, and it is the seconds per cycle. Okay, this is the time for one cycle of the object, whatever it happens to be. Okay? The inverse of period is frequency. And frequency is how often something happens. It's symbolized by a small or lowercase f, and it is cycles per second, which we sometimes abbreviate hertz. So these two things are the inverse of each other. Okay? Seconds per cycle, cycles per second, which means period is 1 over f, and f is 1 over t. They are the inverse of each other. Okay, so as an example, if I had something that had a period of 4 seconds, that means it takes 4 seconds to make one cycle. Everybody okay with that? Yes? Okay, so what would the frequency of this be? One cycle over, so 1 over 4. Okay, so that means that it's, well, it'd be one cycle every 4 seconds, but it's actually going to be then 1/4, okay, hertz. Because if it takes 4 seconds to make one complete cycle, that means it only makes 1/4 of a cycle per second. Right? It takes 4 seconds to make a complete cycle. That means that after 1 second, it'll have only made 1/4 of a cycle, 0.25 hertz, or 1/4 hertz. Okay, so let's look at this question here. We have the wheel of a car has a radius of 0.29 meters. So they told us what R is, 0.29 meters. Okay, it's being rotated at 830 revolutions per minute. Did they give me a frequency or a period there? They gave me revolutions per minute. Is that period or frequency? It's frequency because it's revolutions per time interval. Okay, if it was period, they would have told me how many seconds it would have taken for one cycle. Right? So they're telling me the frequency is 830 revolutions per minute. Okay? We want to determine the speed at which the outer edge of the wheel is moving. So the formula we have is that V equals 2 pi r over t. Okay? I don't have t, I have f. Okay? But I do remember that f equals 1 over t. Are you okay with that? Okay. So if I look at this formula, could I say that this is 2 times pi times r times 1 over t? Yes. So could I also then say that that would be true. Right? If f is 1 over t and t is already on the bottom, I'm dividing by t or I'm multiplying by f. It's the same operation because they're the inverse of each other. Okay? Follow my reasoning here? Okay, I'm going to go back down here because I see some people not understanding it. So f is equal to 1 divided by t. Okay? And right now, t is being divided by, right? I'm dividing this formula by t. So that's the same as saying 2 times pi times r times 1 divided by t, right? Because multiplying by 1 won't change the top any. Right? 1 over t equals f. So really, all this is saying is 2 times pi times r times 1 over t, which is the frequency. So multiplying by the frequency is the same as dividing by the period. All right, so I've got r, I've got f, and now I have a formula. 2 times pi times r times f. Can I calculate the speed of the wheel? Okay, so I'm going to plug in those numbers. Okay, I could do this, or I could just go t equals 1 over f, find out what t is, and plug it into the other formula. Plug it in like this. Okay, I could do that too, but it's an extra step and I don't want to do it. Okay, so we're going to have 2 times pi times 0.29. They told us the radius was 0.29, and then multiplying by the frequency. Now, here's the problem. This 0.29 is in meters, and then my frequency is in revolutions per minute. So I'll get a speed that's in meters per minute. Is that something we typically use? Okay. What should I do to this 830 RPMs to get it into be rotations per second? Divide by 60. Okay, so I'm going to do that as well. Okay, so 830. All right, so that wheel spins around 13.83 times in 1 second. Okay, fast. Okay, that's a lot of spins. All right, so now I've got that. So I'm going to punch that in here, 13.83. And we'll get the speed that the wheel is rotating. So times 2 times, should I use 3.14 or should I use the full value of pi? Full value of pi. It's right there. Okay, times 0.29. Okay, so the wheel is spinning at 25 meters per second. Oh, not multiple. Sorry, supposed to multiply. Okay, so that means it's spinning at 90 kilometers an hour. Okay, on the tire spinning machine. And that's important because actually there are a number of different speeds if something's not balanced that it would oscillate at. Okay, usually they're progressive. So you don't usually feel it until it's like at 80 to 100 kilometers an hour, but there would be lower speeds and higher speeds at which it would also resonate. Okay, you just tend to notice it at higher speeds. Okay. So that's how we calculate the speed using this formula, okay, of something moving around and around in a circle. Okay, so that's what we just did. Let's skip that. All right. So the things we have to remember about something moving in a circle is that the velocity's magnitude doesn't change. Okay, it's traveling at a constant speed. But because it's moving in a circle, its direction is constantly changing. Okay? If the force that's keeping it in the circle disappears, then it travels in a straight line. Okay. So let's have a look at what that looks like. Okay. Now, let's see. Like if you're whirling something around and around in a circle, can you get it going faster than you could throw it?
Yeah.
Absolutely. Okay. So what weapon utilizes that? Sling. Exactly. Okay, so if I'm whipping this thing around, I mean that's moving way faster than I could ever hope to throw. Okay, I can only throw something as fast as my arm can move. Okay, so I could get something moving a lot faster if I'm spinning it around and around. Right, so hence the idea behind the sling. Right now, the Bible says that David killed a man with a sling. Okay, with a rock thrown from a sling. Okay? And lots of people go, oh, there's no way that that could have happened. There's no way. Okay? I actually have a video, the History Channel did this thing where they actually proved scientifically that, yes, a small, let's say 14-year-old, 13, 14-year-old boy, David, could have actually killed someone with a rock from a sling. Okay? So it proved it scientifically. So I'm actually going to show you that video now because it uses the same principle. Right? When we let go of that sling, okay, then the rock flies out in a straight line. Now that's not as easy as it sounds. Right? The design of a sling is so that it's got basically a loop that goes around one of your fingers. Okay? And then it's just a strap, basically, that the rock goes in, and you hold the other end of the strap. So you whirl this thing around and around the circle, and then you let go of this little knot that's tied in the strap. When you let it go, the force that was holding it in the circle, which is the tension in the strap, is gone. And now that rock flies off in a straight line from that point. Okay? Everyone with me there? Okay, now you can get this going really, really fast. Okay? Same for a whip. Okay? Now what sound does a whip make when you roll around and crack it out? Right. Okay? You guys know what that sound actually is? Yeah, it's the tip of the whip breaking the sound barrier. It's a small sonic boom. Okay? And the same is true for a person using a sling. Okay? If you use a sling to throw a rock and you're good enough at it, the end of the sling will crack the sound barrier. And the rock is also traveling pretty close to the speed of sound when you use the sling. Okay? That's pretty impressive. Okay? All right. Okay, so if something is going to move in a circle, we've already said that it's not following Newton's first law. Okay? It is actually changing its velocity, and any change in velocity is accelerated motion. So something moving in a circle is undergoing uniformly accelerated motion. The acceleration and the force, according to Newton's second law, are always in the same direction. Okay? So if the object is being pulled towards the center, then it's accelerating towards the center. Okay? We call that centripetal acceleration. Okay? Which probably sounds like a word you've heard before, but isn't exactly the same. You guys have probably all heard of centripetal acceleration. Okay? When people say centrifugal force, centrifugal speed. Okay? Centripetal and centrifugal are opposite. Okay? Centrifugal means center fleeing, or going away from the center. Centripetal means center seeking. There's actually no such thing as centrifugal force. There aren't any forces that are trying to pull an object straight out of a circle. Okay? There's inertia. Inertia will let the object travel in a straight line tangent to the circle. Okay? But it's not a force. It's just the natural tendency of the object. The only force that's actually present is the one that's pulling it back towards the center all the time. There are no forces that are trying to pull something directly out of a circle. That would mean that there's a force doing this. Okay? There are no forces trying to pull something in that direction. Okay? Therefore, centrifugal force is actually not real. Okay? What it is really just inertia, which is not a force. All right, so centripetal acceleration depends on two factors: the speed of the object and the radius of the circle. Okay, so according to this formula, the centripetal acceleration experienced by an object is equal to the speed of the object squared divided by the radius of the circle. So the faster the object goes, the greater the acceleration it experiences. In what way? Linearly or exponentially? Exponentially. Right? So think about that when you're going around the exit ramp out here, okay, trying to get back onto Highway 2. Okay, if you're going around that exit ramp, which is a circle, okay, if you double your speed around that circle, you don't require twice as much force to keep you in that circle. You require 4 times as much force to keep you in that circle. And you're relying almost entirely on friction to do it. Okay? So trying to take that 60-kilometer-an-hour corner in 120, okay, would be crazy. Okay? I'm not saying it couldn't be done if you had the right car and the right driving conditions, but okay, you would require 4 times as much centripetal force to keep you in that circle by doing it. Okay? And of course, if you've ever gone around that, you know that when you go around, you're kind of thrown to the outside. Okay, you guys all experience that? Okay, if you drive with somebody who drives really crazy and takes corners really fast, okay, you kind of feel thrown towards the outside of the corner. Well, you're not being thrown out of the circle. You're trying to travel in a straight line. Okay, the door and your seat belt and whatever else prevent that. Okay? They're preventing your inertia from allowing you to do what you're supposed to do. Okay, everybody with me there? Right. Now, if I make the circle bigger, that is, I increase the radius, what will happen to the centripetal acceleration? It'll get smaller. So if I take a corner wider, is there a better chance I'll stay in it? Yes. Okay? And that's what race car drivers usually try and do when they're going around a corner. So if this is the corner that they're trying to go around, what they typically do is they try and come in from the outside, kind of towards the inside, okay? And they increase the radius of that corner. Rather than trying to hug the inside, they essentially make the corner or the circle a little bigger, okay? Allowing them to maintain their cornering. Increase the radius of the corner by taking it kind of like that. Okay. So for centripetal acceleration, we have an exponential relationship with speed. Speed goes up, the acceleration goes up exponentially. If the radius goes up, the acceleration goes down in a exponential or linear way. Linear, right? Because r isn't squared. Right? So if I have twice as big a circle, I'll have half as much centripetal acceleration. All right, so centripetal acceleration is a vector quantity, always towards the center. Okay, so that direction is always the same, towards the center of the circle. Now, if we're looking at, for example, the moon orbiting the Earth, okay, what keeps the moon in orbit? Gravity, the Earth's gravity. Okay, so the Earth's gravity is always pulling the moon towards the center of the Earth, but the moon wants to do this. Okay, but as it moves through that circle, okay, so it wants to do this, okay, the moon, or sorry, I should draw it over here. So the moon wants to go this way, but the Earth pulls it, okay, and it keeps pulling it back towards the center. It's always changing that vector, okay, always altering it so that the moon travels in a circle rather than flying off. Everybody with me there? Now, is the moon's orbit a perfect circle? The moon's orbit is not a perfect circle. In fact, it's elliptical, and in fact, that circle's changing all the time. What's the moon always doing? Yes, very slowly. But it's also getting farther away all the time. The moon is actually escaping Earth's gravity by about 2 centimeters a year. Okay, but the moon's been orbiting the Earth for about 4 billion years or so. It's had time to get a lot further away in that time. At 2 centimeters per year, it adds up. Okay, but obviously the moon used to be a heck of a lot closer to the Earth, and that actually had a lot of implications for the Earth's rotation, the Earth's orbit, seasons, the tilt of the Earth. All of that stuff is actually influenced by the moon's gravity and the moon's rotation.
If the moon was closer, if you were under the moon, would you be lighter?
The moon would have to be really, really close for you to notice that, but it is true that that would be the case. So when the moon is directly overhead, yeah, we're all a little tiny bit lighter. Not enough to make any difference of any kind, but yes. Yes, that's what causes the tides, right? The moon pulls the ocean towards it. The whole ocean moves over to one side of the world.
So if the moon was closer to the Earth, does that mean the waves would be much bigger?
The tides would be much bigger, yes, and more often. Okay, because if the moon was closer, it wouldn't take as long for it to go around the Earth either. So if you go back 3 billion years, okay, then yeah, tides would have been way bigger, way more frequent. Like the ocean would be going back and forth, and the moon would go around a couple of times a day, as opposed to once every 29 days, 29 plus whatever days. Then you would have all kinds of weird tidal shifts. Okay, so if you're looking at Jupiter, for example, Jupiter's got lots of moons, right? But it's kind of got the big Galilean moons, and the one that's closest to Jupiter, Io, is the one that's covered in volcanoes. Right? And the reason for that is Jupiter's always pulling on it, but so are all the other moons, and so it's constantly it's almost like it's made of clay and it's being squished and pulled all the time, which is what keeps it so hot in volcanic. All right, actually, I've got a video on that that will work, because I watched it just on Friday with Mr. Dickey. Okay,
So, since the Earth is stretched because of the moon, does that also mean that we are taller at certain times of the day?
theoretically, yes. Yeah. Okay, but again, like we're talking about something we haven't talked about yet. We'll talk about later in the unit, and that is that the force of gravity between two objects is calculated using this formula. Okay, so the force of gravity that anything experiences is based on the mass of the two things involved. If we're talking about ourselves, that is an incredibly small mass. So the force between us and the moon, for example, would be really, really small for two reasons. We're really small. The moon is small compared to the Earth. And the distance between us and the moon is incredibly big. And we're dividing by that number squared. Okay? So yes, we would be slightly taller if the moon was directly over us. But so little that we'd never be able to do that. Right? But when we're talking about how much the moon pulls on the Earth, we're talking about two masses that are much bigger. And so there, the force of gravity between them is much bigger. Yeah?
So if the moon got tidal locked on like the Earth's orbit or whatever, would that mean that all of Earth's water would be pulled to that side of the Earth?
Yes. So there wouldn't be tides anymore. It would be high tide where the moon is and low tide everywhere else. Yeah.
Fun.
Since the moon is 70 years every year,
Yeah.
would it mean that it means like get out of Earth?
Theoretically, yes. If the moon gets far enough away, the force of gravity between the moon and the Earth would be weak enough that the moon could fly off. It probably won't before the sun swallows it up. Okay, because the sun is going to go through an aging process where it expands and it'll go out almost to Mars. Okay, it gets that big as it ages. That's billions of years away. Don't worry, it's not happening tomorrow. Okay? But it is going to get bigger and it'll get big enough to swallow out the Earth before the moon ever has a chance to swallow it up. Okay, so centripetal acceleration here. Okay, we've got maybe this one on the slings will still work.